Hello and welcome back. Titration is a tricky subject, so one of the things that best prepares you for figuring out titration problems is doing a bunch of titration problems. So this video is just several titration problems all in a row. That's all it is, okay? So number one, what's the pH of 100 milliliters of 0.1 molar hypochlorous acid solution after titration with 60 milliliters of a 0.2 molar potassium hydroxide solution? So Step one. Step one is always to find the equivalence point to see whether we're before it, at it, or after it, because those three calculations are very different. So let's find the equivalence point. We've got 100 milliliters of 0.1 molar hypochloric acid. That is 10.0 millimoles of our acid. We've got our base, which is 60 milliliters. There we go, of 0.200 molar. 6 times 2 is 12. And so we have 12.0 millimoles of OH minus. So we actually have more base than we have acid, which means we are after the equivalence point. As soon as we know we're after the equivalence point, we're like, oh, that is our excess base assumption. And we're going to say that the OH is going to dominate the production of base, and so we are going to be calculating the concentration of that OH to get a POH to get a pH. We're going to ignore the OCl minus that's there because it's a weak base in comparison to our strong base. So our excess base is our 12 millimoles minus our 10.0 millimoles of acid that reacts, and so we have 2.0 millimoles of OH. And we're going to go ahead and convert that to a concentration by dividing by the total volume, which is 2.0 millimoles of OH divided by 100 milliliters plus 60 milliliters. Woo! I love it when it just scrolls for no particularly good reason. OH minus is, what is that concentration? That is going to be 0.0125 molar. Our POH is just the negative log of that. We don't put the molar in there. We divide by reference concentration. And you get 1.90. And our pH is 14 minus 1.90, or 12.10. So there we go. 12.10, answer B. Next one, titration practice number 2. What's the pH of 50 milliliters of 0.1 molar nitrous acid, with a Ka value given there, after the addition of 60 milliliters of 0.1 molar sodium hydroxide? What'd you come up with? Find the equivalence point. 50 milliliters times 0.100 molar of our acid is going to be 5.0 millimoles of acid. Our base is 60 milliliters times 0.100 molar OH, which is going to be 6.00 millimoles. And we are going to figure out, oh, look, once again, what do we have? Once again, we have the excess base. I mean, this is like almost boring, right? So we have excess base, just like we did in the last problem. 6.00 millimoles of OH minus our 5.00 millimoles of H plus is going to be 1.00 millimoles of OH. Then we're going to go ahead and try and turn that into a concentration. It is 1.00 millimoles of OH divided by 50.0 plus 60.0 milliliters. And we get that 1 divided. I've seen this problem a few times now. 0.090, molar, and we get our POH is 2.04, and our pH is 11.96. We've seen that number several times. Okay. It just happens to come up. I didn't do it on purpose. So there we go. Again, finding out whether you are before or after the equivalence point is the quickest way to know what to do, because there's only 3 different things to do once you've started adding base. after the equivalence point, at the equivalence point, and before the equivalence point. What is the pH of 50 milliliters of 0.1 molar nitric acid after the addition of 25 milliliters of 0.1 molar sodium hydroxide? Righty then. Okay, let's find the equivalence point. This one we probably could do just by inspection, even if we don't actually calculate it, right? 50 milliliters of 0.1 molar, 25 milliliters of 0.1 molar. Since we have identical concentrations, then identical volumes would be the equivalence point. Since we have less OH, we know we are before the equivalence point. But you could calculate it if you wanted. And you'll find that you're before the equivalence point. So what do we do before the equivalence point? We use the Henderson-Hasselbalch equation with the addition of the acid and base as we have our reactions. We have HNO2 plus OH minus makes NO2 minus plus H2O. That's the actual reaction that's happening. Our acid is reacting with the OH minus. BRI. Why BRI and not ICE? Because we have a strong reaction. We have a strong base present. Anytime you've got a strong acid, strong base present, you're going to do the BRI part to get rid of that before you try to do any CE or ICE part. What do we have? Well, since we have volume changing, let's do things in millimoles. If you multiply 50 times 0.1, you get 5.00 millimoles of that. If you multiply 25, you get 2.50 millimoles of that. You should show your work on those. Since we're doing a bunch of these in a row, I'm going to skip the work. But you guys should show your work on a test, because I only know you know what you're doing if you actually show me what you're doing. None of that. We don't care about water because its concentration doesn't change. We're going to react all of our hydroxide because we can. As much of it as possible is going to react. So minus 2.5, minus 2.50, and 2.50. So we get 2.50, 0, and 2.50. And so what do we have? We have all of those as millimoles. And they're equal amounts. And if you remember, there's something special that happens when you have equal amounts of base and acid. But let's go ahead and use the Henderson-Hasselbalch equation. pH equals pKa plus the log of A minus over HA. And so we get our pKa is 3.34, and our log, remember the nice thing about the Henderson-Hasselbalch equation is it works with concentration, it works with moles, and it works with millimoles. So 2.50 over 2.50 millimoles, doesn't matter which one because they're the same, so we don't even have to try to figure that one out. And so we just get a 3.34. And so we get answer C here. All right, before the equivalence point, Henderson-Hasselbalch equation after running your strong reaction using a BRI table. Righty, let's do some more here. What is the pH of 50 milliliters of 0.1 molar nitrous acid after the addition of 50 milliliters of 0.1 molar sodium hydroxide? So, where are we? 50 times 0.1, 50 times 0.1, those two are going to be equal. We are at the equivalence point. Since we started with 50.0 milliliters times 0.100 molar HNO2, that means we have 5.00 millimoles of HNO2. I could run the reaction. I could actually write out the reaction right here, the HNO2 plus OH, whatever, and I find that 100% of it is going to make NO2 minus, because that's what the equivalence point means. We've used up all our acid. So I also know that I have 5.00 millimoles. So we're at equivalence point. So we also have now, after our reaction, we have 5.0 millimoles of NO2 minus. And so now we're going to go ahead and set up a system where we're going to calculate what is the pH of 5 millimoles of NO2 minus divided by, right, we need concentration, 5.0 millimoles divided by 100 milliliters, right? That's addition of our two things there. 5 divided by 100 is 0.050 molar NO2 minus. That's what we have. We're given a Ka. If we remember, we're going to want a Kb. So we go ahead and plug that Ka in there. We find that Kb is, where is it? 2.17 times 10 to the minus 11th. What do? We plug that in. We're going to write our NO2 minus plus water goes to HNO2 plus OH minus. We got our ICE. NO2 is 0.050 molar. We don't care about water. We have none of that, approximately none of that. Minus x, 0.050 minus x. Looks very similar to everything else we've done. Right? It starts to look very familiar. Equals x squared over 0.050 minus x. Why are we going to use a small x? Because we have a concentration of 0.05 and we have a k of 10 to the minus 11. So we're going to use a small x and we get x squared over 0.050 is 2.17 times 10 to the minus 11th. Multiply both sides by 0.05. Take the square root. You get x is equal to 1.04 times 10 to the minus 6. Okay, 1.04 times 10 to the minus 6 is our OH minus concentration. You're like, 1.04 times 10 to the minus 6. That's actually not all that far off of what is pure water? 1.0 times 10 to the minus 7th, right? So we know that we're going to be off a little bit because we made the assumption that our OH was essentially 0, but it's actually going to be somewhere around 1 times 10 to the minus 7th in there. And so it's actually going to affect the, wrong thing. It's actually going to affect the second digit here. So it's going to be 1.1 times 10 to the minus 7th, roughly. We'd actually have to do the calculations. So we know that our pH isn't going to be perfect. But remember, even when you double concentration, pH changes by about 0.3. And so if we're off by 10%, our pH might change by like 0.01, 0.02. But we should be aware of that. Now, we could actually put in our 10 to the minus 7th into our ice tables and actually solve that either exactly by using quadratic formula or by using Wolfram alpha or some other solving thing. And I'll tell you what the answer for that is. But anyway, we get x equals 1.04 times 10 to the minus 6. That's our concentration of OH minus is 1.04 times 10 to the minus 6 molar. And so we plug that in. The log of 1.04 times 10 to the minus 6 is our POH is 5.983. And our pH is 14 minus that. And so we get 8.02. Now, if you do put in the 1 times 10 to the minus 7th here instead of 0, and you solve this exactly, you get a pH of 8.0. So instead of 8.02, you get 8.0. So we're going to be awfully close. So even when our assumptions aren't perfect, the nice thing about pH is it kind of smooths out percentage differences in things. That's also a bad thing about pH, right? If we really care about the concentration of H+, right, pH off by 0.3 means we've doubled the concentration, and that's a pretty big difference. Right, so there's one more problem. What did I forget to do? What did I forget to do? I forgot to check my assumption. Was my assumption good? 10 to the minus 6 compared to 10 to the minus 2. Assumption is obviously good. 4 orders of magnitude. We can say that that's an obviously good assumption. Comparing, right, our x, 1.04 times 10 to the minus 6, to our initial concentration, 0.05. All right, another one. What's the pH of titration? 37.5 milliliters of 0.34 molar butanoic acid is titrated with 35 milliliters of 0.409 molar sodium hydroxide. Like, this one's a little harder to look at and know exactly where we are. So let's go ahead and do our calculation. 37.50 milliliters times 0.350 molar is 13.125 millimoles of my acid. 35.0 milliliters times 0.409 molars is 14.315 millimoles of base. And oh, look at that. We have more base than acid, which means we're after the equivalence point. And we can just use the excess base assumption. I forgot to give you my funny face. Sorry about that. I'll still pause it there, but sorry about the no funny face. After the equivalence point, how much? 14.315 minus 13.125 millimoles H plus millimoles OH That gives me 1.190 millimoles of OH minus. We got to find a concentration for that. 1.190 millimoles OH minus divided by my total volume is 37.5 plus 35.0 milliliters. And that gives me a concentration of 0.0164 molar OH minus. My POH is going to be 1.785. My pH is 14 minus that is 12.215. If I look back up at my K value only has two significant figures, so I get 12.22. And that is answer A. All right, that was a bunch of problems. We practiced titration in many different ways, and hopefully you got a good sense of it. Always find where you are relative to the equivalence point first, before, at, or after, and then try to figure out which calculation you need to do. Thanks so much.